When establishing a grounding plan for a 400 amp single-phase service drop on a yard pole, supplying power to two 200 amp disconnects, one for the house and one for a machine shed, several key steps should be followed. These steps pertain to grounding electrodes, grounding conductors, service entrance conductors, disconnects, and equipment grounding. Firstly, at the yard pole, install two grounding electrodes. The first should be an 8-foot copper-clad steel rod driven into the earth. The second electrode should be a grounding ring encircling the pole, positioned at least 18 inches below grade. Bond these grounding electrodes together utilizing a number 4 American wire gauge copper conductor. Extend a number 4 American wire gauge copper grounding conductor from the yard pole electrodes to each of the building disconnects. This creates a common grounding point for the entire system. As for service entrance conductors, install a 4-wire service entrance cable from the yard pole to each building disconnect. The conductors should include two 1/0 American wire gauge or larger phase conductors, typically colored black and red, one 1/0 American wire gauge or larger neutral conductor, typically colored white, and one number 4 American wire gauge or larger grounding conductor, which can be green or bare copper. At each building, install a 200 amp disconnect at the yard pole and at each building. Bond the equipment grounding terminal of each disconnect to the number 4 American wire gauge grounding conductor that originates from the yard pole electrodes. Connect the equipment grounding conductors from all electrical equipment within the buildings to the equipment grounding terminals of their respective disconnects. This ensures that all non-current carrying metal parts are properly grounded. Additional considerations include firstly maintaining a 4-wire configuration throughout the entire system if the previous service was also a 4-wire system. Secondly, ensure proper bonding between all metal components of the electrical system. This includes conduits, enclosures, and equipment frames. This bonding creates a low impedance path for fault currents, facilitating the operation of overcurrent protection devices. Thirdly, it is essential to obtain all necessary permits and inspections from the local electrical authority. These inspections ensure that the installation complies with local codes and regulations. A detailed explanation of grounding electrodes is necessary for a thorough understanding of their role. Grounding electrodes are conductive objects buried in the earth to provide a low impedance connection to ground. The purpose of a grounding electrode system is to stabilize voltage to earth during normal operation and to limit the voltage rise created by ground faults. The 8-foot copper-clad steel rod is a common type of grounding electrode. It should be driven vertically into the earth until only a small portion remains above ground. In areas where bedrock or large rocks prevent vertical installation, the rod can be buried at an angle not exceeding 45 degrees from vertical or laid horizontally in a trench at least 30 inches deep. The grounding ring, another type of grounding electrode, consists of a bare copper conductor at least 20 feet long, buried in a circle or U-shape at least 18 inches below grade. The grounding ring provides a larger contact area with the earth compared to a ground rod, potentially lowering the ground resistance. The number 4 American wire gauge copper conductor used to bond the grounding electrodes together ensures that they function as a single grounding system. This conductor should be securely connected to each electrode using appropriate connectors listed for direct burial. The extension of the number 4 American wire gauge copper grounding conductor from the yard pole electrodes to each building disconnect establishes a continuous grounding path. This conductor serves as the primary grounding electrode conductor for each building. The 4-wire service entrance cable is critical for providing both power and a safe grounding path. The 2-phase conductors carry the electrical current to the buildings. A neutral conductor provides a return path for unbalanced loads. The grounding conductor provides a low impedance path for fault currents, protecting against electrical shock hazards. The selection of 1/0 American wire gauge or larger conductors for the phase and neutral conductors is based on the ampacity requirements of a 200 amp service. The ampacity of the conductors must be sufficient to carry the expected load, considering factors such as voltage drop and ambient temperature. The equipment grounding terminal in each disconnect serves as the central grounding point for the building's electrical system. Connecting the number 4 American wire gauge grounding conductor from the yard pole electrodes to this terminal ensures that the building's grounding system is connected to the main grounding electrode system. Equipment grounding conductors from all electrical equipment within the buildings must be connected to the equipment grounding terminals of their respective disconnects. These conductors, typically green or bare copper, provide a path for fault currents from the equipment back to the source, allowing overcurrent protection devices to trip and clear the faults. Proper bonding of all metal components of the electrical system is essential for safety. Bonding involves connecting all metal parts together to create a continuous electrical path. This path ensures that all metal parts are at the same potential, minimizing the risk of electrical shock. Bonding can be achieved using bonding jumpers, clamps, and other approved methods. Finally, obtaining all necessary permits and inspections is crucial for ensuring compliance with local electrical codes and regulations. The local electrical authority will review the plans for the electrical installation and conduct inspections to verify that the work is performed correctly and safely. This process helps to prevent electrical hazards and ensures that the electrical system is installed in accordance with applicable standards. Understanding the NEC, or National Electrical Code, is crucial for ensuring a safe and compliant electrical installation. Several sections of the NEC are particularly relevant to grounding and bonding. NEC Section 250 covers the general requirements for grounding and bonding. It provides detailed information on grounding electrode systems, grounding conductors, equipment grounding, and bonding methods. NEC Section 250.24 specifically addresses grounding of service entrance equipment. It outlines the requirements for connecting the grounding electrode conductor to the service equipment and the grounding electrode system. NEC Section 250.32 covers grounding requirements for separate buildings or structures. It provides guidance on whether a grounding electrode system is required at each building and how to connect the grounding electrode system to the main grounding electrode system. NEC Section 250.50 addresses the grounding electrode system. It specifies the types of grounding electrodes that are permitted and the requirements for installing them. NEC Section 250.66 covers the size of the grounding electrode conductor. It provides a table that specifies the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. NEC Section 250.92 addresses bonding of equipment containing over 250 volts to ground. It requires that metal enclosures and other conductive parts be bonded together to create a low impedance path for fault currents. NEC Section 300.3 covers conductors of different systems. NEC Section 310.16 provides ampacity tables for conductors. These tables specify the allowable ampacity of conductors based on their size, insulation type, and installation conditions. When implementing a grounding plan, consider several additional factors that can affect the effectiveness of the grounding system. Soil resistivity is a measure of how well the soil conducts electricity. High soil resistivity can increase the resistance of the grounding electrode system, reducing its effectiveness. Soil resistivity can vary depending on factors such as soil type, moisture content, and temperature. In areas with high soil resistivity, it may be necessary to install additional grounding electrodes or use ground-enhancing materials to lower the ground resistance. The proximity of underground utilities can also affect the grounding system. Underground utilities such as gas pipes, water pipes, and communication cables can provide alternative paths for fault currents. It is important to maintain adequate separation between grounding electrodes and underground utilities to prevent interference or damage. The presence of stray currents in the electrical system can also affect the grounding system. Stray currents are unwanted currents that flow through the earth or other conductive paths. Stray currents can cause corrosion of metal components and can also interfere with sensitive electronic equipment. It is important to identify and mitigate the sources of stray currents to ensure the proper functioning of the grounding system. Regular testing and maintenance of the grounding system is essential for ensuring its continued effectiveness. Ground resistance testing should be performed periodically to verify that the ground resistance is within acceptable limits. Visual inspections should be conducted to check for signs of corrosion or damage to grounding electrodes, conductors, and connections. Any damaged or corroded component should be repaired or replaced promptly. Furthermore, it is critical to select the appropriate materials and equipment for the grounding system. Grounding electrodes should be made of corrosion-resistant materials such as copper or copper-clad steel. Grounding conductors should be sized appropriately for the fault current they are expected to carry. Connectors and clamps should be listed for use with grounding conductors and should be installed according to the manufacturer's instructions. Ground-enhancing materials can be used to improve the conductivity of the soil around grounding electrodes. These materials typically consist of a mixture of conductive minerals and chemicals that help to lower the ground resistance. When using ground-enhancing materials, it is important to follow the manufacturer's instructions carefully and to ensure that the materials are compatible with the soil conditions. Consider the impact of lightning strikes on the grounding system. Lightning strikes can inject large amounts of current into the grounding system, potentially damaging equipment and creating safety hazards. Lightning protection systems should be installed to protect against lightning strikes. Lightning protection systems typically consist of air terminals, down conductors, and a grounding system. The grounding system for a lightning protection system should be separate from the grounding system for the electrical system. It is crucial to document the grounding system thoroughly. Documentation should include a diagram of the grounding system showing the location of grounding electrodes, conductors, and connections. Documentation should also include the results of ground resistance testing and any maintenance or repairs that have been performed. This documentation will be helpful for future inspections and maintenance. Furthermore, it is good to consider the long-term maintenance of the grounding system. Over time, grounding electrodes and conductors can corrode or degrade, reducing the effectiveness of the grounding system. Periodic inspections and testing should be performed to identify any problems and to ensure that the grounding system is functioning properly. Replacement of grounding electrodes and conductors may be necessary to maintain the effectiveness of the grounding system. It's also important to stay up to date on the latest electrical codes and standards. Electrical codes and standards are constantly evolving to reflect new technologies and safety concerns. It is important to stay informed about the latest changes to the electrical code and to ensure that the electrical system complies with the current requirements. This can involve attending training courses, reading industry publications, and consulting with electrical experts. In summary, a comprehensive grounding plan for a 400 amp single-phase service drop requires careful attention to detail and a thorough understanding of electrical codes and standards. Firstly, install appropriate grounding electrodes and bond them together. Secondly, run properly sized service entrance conductors to each building disconnect. Thirdly, connect equipment grounding conductors to the equipment grounding terminals. Then, ensure proper bonding of all metal components, obtain necessary permits and inspections, and perform regular testing and maintenance. By following these steps, you can ensure a safe and reliable electrical system.